Okay, so we're at part 5 on beams. We've gone through quite a bit. We've figured out how to do external loads. We've now started to do internal loads. I got a real treat for you today, which is I'm going to tell you the question type that most students get wrong. So if you can do all that other stuff, there are a few questions that come up where you're doing internal loads and you're dealing with distributed loads at the same time, and students tend to make mistakes. So we have kind of a complicated problem that we're going to work at, and I'm going to explain to you where most of the students break down, and hopefully if you're faced with a question like this, you'll have a good strategy for how to approach it. Okay, so first thing, we have a beam and it has a distributed load all the way across. And I'm asking you to find V and M at the midpoint of the beam. Well, it just happens that the midpoint of the beam is where we have a distributed load. And there's one more little kind of thing we got to think about when we're doing internal loads around distributed loads. Anyway, so let's work away at it and see how we do. So, first thing that we'll do is just take a look at our problem. Now, I've left it with different units. So we have pounds and feet in this, and we don't have to convert it over to meters and newtons. If we follow the same patterns and we are consistent with our units, then it doesn't matter if we're doing pounds, feet, anything. We're okay with those units. So the units isn't what is my concern so much in this problem. Okay, so I'm ready to go with my problem. So first thing that I want to do is work at my external loads. So before I dive into any internal loads, I have to figure out my external loads. And the first thing that I'm going to do is my distributed load. So I have 300 pounds per feet times, I guess, 5 plus 11, so 16 plus 4, so 20 feet. It spans 20 feet. And I guess that 300 times 20 would be 6,000 pounds. Okay. Step number 2 is going to be to draw a free body diagram. So draw my free body diagram up here. And I have an unknown of A. I have 4,000 pounds here. I have my 6,000 pounds, which is my equivalent for my distributed load. I have 8,000 pounds here, and I have D over there. Okay, 3. Pick a point. Okay, and I think in this case I'm going to pick point A. It meets my criteria, it's an unknown, and it's at one of the ends. From there, do some distances. So to 4,000 is 5 feet, 6,000 is 10, oops. 8,000 is 16, and all the way across to D is 20. 16. Okay. Step 5, sum of moments. So sum of moments clockwise has to equal sum of the moments counterclockwise. From my pivot point as I work across, A is at a distance of 0, so it doesn't go into my calculation. I have a counterclockwise of 4,000 at 5 feet. I have plus 6,000 at 10 feet. Keep going. Okay, that's going to keep trying to turn clockwise. So plus 8,000 at 16 is going to be equal to D at a distance of 20. So 4,000 times 5 is 20,000, plus 6,000 times 10 is 60,000, plus 8,000 times 16 gives me a grand total of 208,000, I guess, feet. Oops. Pound-feet is equal to D at 20 feet. And that divided by 20, so 10,400 pounds is equal to D. Step number 6, sum of forces. So nothing tricky yet, so just the same process that we're going through, finding our external and internal loads. So A plus D is going to be equal to 4,000 plus 6,000 plus, I think that's 8,000. So A plus 10,400 is equal to 18,000. A is equal to 7,600 pounds. Okay. Here's where mistakes are made. When we go to find our internal loads, what we want to do is we want to cut the beam. Okay. Often students will want to cut this beam. However, that is not our beam. Our beam is this beam. If we were to cut the beam over here, then what's going to happen is we're going to cut it, and we either include the entire distributed load right at the middle, or we exclude the entire distributed load. But what we actually have to do is cut our beam down the middle, and we have to have a left-hand side which has a distributed load, or a right-hand side which has a distributed load. So we're going to have an extra bit of distributed load to work at, but if we don't, we're going to get the wrong answer, and we've wasted all of our time. Okay, so let me just transcribe these over. So my force at A, 7600, and my force at D, 10400. And here we go. So I think I'm just going to decide I'm going to take the left-hand side, and my left-hand side is going to look like this. I've got a distributed load across the entire length, and it's 300 pounds per foot. My beam is 10 feet in length. So what that means is my equivalent load for the left-hand side is going to be equal to 300 pounds per foot times 10 foot-feet is equal to 3,000 pounds. Okay, and it would be at the midpoint, so 5 feet. So my left-hand side, once I change my distributed load for the left-hand side to an equivalent load is going to look like this. 7,600 pushing up, 4,000 pushing down. My equivalent load, I'm going to lay it out just in a second, but I'll have 3,000 to put in there as well. And then I have my cut. So in this case, I'll put in my V, and I'll put in my M. Since the whole thing is 10, and this guy is 5 here, that means actually my 3,000 is also at the same location. So I have 4,000 and I have 3,000, or I guess I have a total of 7,000 at that point. Five feet to the cut, and as well my cut total length across is 10. Sum of forces up is equal to sum of forces down. Up 7,600 is going to be equal to 4,000 and 3,000 at the same spot. Those are added together, so 7,000 plus V. V is going to be equal to 600 pounds. Sum of moments in one direction has to equal sum of moments in the opposite direction. Start at my pivot point. There's always an M there. So M over here. 7,000 at a distance of 5. That's going counterclockwise. Keep going across. 7,600 at 10. That's going clockwise. So 76,000 minus 35,000 is going to be equal to M. And 41,000 pound-feet is equal to M. Okay, so really the careful thing that you have to take is if you have a distributed load that is in the middle of the object or where you're slicing, don't just keep going from the external load work you were doing. You've got to backtrack right to your starting point. There's definitely some questions like this that come up in your TSSA exams, so just make sure you're careful with this stuff. If you have a slice right through it, you got to backtrack if you're going to find the right answer at the end. So if there is a distributed load that we cut through, we don't use the equivalent load. We use to find the external reactions because it incorporates potentially both the left and right hand side. When we find the internal loads, we have to cut the beam first and go back to that original beam in order to find the new left hand or right hand side that we're going to work from. Okay, so we've seen some complicated internal load calculations. Let's talk about what happens with external loads. So when we have a failure that occurs, we have a main failure mechanism for metal objects, which is through bending. So if the object is to be bent one way or the other, that's normally the failure mechanism. Metal doesn't shear too easily. Only in limited situations do we have shear as a primary failure mechanism. And when we talk about stress, one of the things we have to understand is where is the maximum stress occurring in a beam. Okay, and so we'll go to the idea that if we take an object and we were to bend it, so we were to bend it up, we would have a case where we have some strain that's occurring. And don't forget what strain is. It's a change of length compared to an original length. So if a length gets shorter, then we have strain. Or if a length gets longer, then we have strain. And so if we look at my object here, which has changed, so I had my original object here, and now after it's been bent, this distance is short and this distance is longer. And because I had a change of length, we've had strain. We also had an equation, E is equal to stress divided by strain, which says that any time that we have strain, we're going to have stress. So when we shorten it, we have a compressive stress that occurs, so at the top of that beam. And at the bottom of the beam, we've stretched it, so we have tensile stress. And we see when we talk about the maximum, we have an amount of stress that gets larger and larger as we go across that cross section of that object. So as it moves through, it keeps getting larger and larger. So I have the shortest or the smallest here in the inside, right? That's my smallest. And my largest is on the outside. And those correspond to areas of maximum stress. My maximum compressive stress on the inside and my maximum tensile stress on the outside. Now for a beam that is symmetrical, the maximum tensile stress will be equal to the maximum compressive stress. One thing that usually we ask is, what happens right at the very center of the beam? Do I have any strain? And the answer is no. Somewhere in between it being the maximum compression and the maximum tension, I have nothing. So there's that transition point. And at that transition point, we have what's known as the neutral axis, okay, or no stress. So that's my area where I have no stress on my object. So if an object is going to break because of it being under lots of stress, and those bonds break away from atom to atom once they are under too much stress, my main failure points on beams are going to be either the top or the bottom surface. So those are my failure points. I have a formula known as the Flexure formula, okay, or the bending stress formula. And what it says is that the stress in the beam is made up of 3 factors. And why we went to the effort of solving for the M value inside of those internal beam questions is so that we could incorporate this into a stress formula. So we had our M, which is one of the primary factors that's going to lead to stress in the beam. So that M value that we calculated is going to go right into that stress calculation. And then we have a couple other things. We have I, which is a measure of how is that material oriented. So we know that if we took a piece of steel and it was flat, it would be easy to bend. However, if we rotated it, it'd be very difficult to bend. And I is a measure of how well organized is the material. It's a second moment of inertia. And C is where am I measuring from? So it's the vertical distance. So it's based off of this neutral axis. So if I'm measuring at the neutral axis, C is 0, which means the stress would be 0. And the further I go, either higher or lower, I get a larger and larger C value, which means my stress value continuously grows as I go up or down in my object. So what that C tells us is that as I go to the outer surfaces, the top or bottom surfaces, I'm going to have my maximum stress. Okay, so maximum stress would be at the top, neutral axis, 0 stress, and maximum tension in the bottom. When we calculated V, that was a measure of us trying to find our shear. And often when we talk about shear, we say shear is going to be our force divided by area. And so that would provide us with an average shear. And that's not entirely true what happens in this system. If we were to look for our maximum stress, the distribution looks a little different. So our distribution of stress actually is more of a rounded profile. And what that means is that the average stress is not too bad of an approximation, but it doesn't find our peak. And our peak stress happens right at the center of the beam. So where the tensile stress or the compressive stress was maximum on the outer surfaces, the shear is maximum on the inner surface, okay, right at that neutral axis. And the maximum shear is in a rectangular object about 50% more than that average shear. So 1.5 V divided by your area gives you the maximum shear. And all different shape sizes of objects, all different shapes of objects have different maximum shear values. So that 1.5 V isn't the same if it was a round shape or it had an I-beam type shape. So every single object is going to have a slightly different maximum shear. Just so happens we often talk about rectangular beams in our applied mechanics class, and in that case 1.5 V gives you your maximum shear in that part. And that wraps up our unit on beams and internal stresses. So a lot of work and a lot of complicated questions. This is an area that is new to a lot of students. So please work hard at this stuff and check in with me if you need help. It's always a challenging subject, and there's a lot to keep track. But keep a good approach to it. So try and remember your steps as I've laid them out to you. And if you can organize your thoughts and keep your steps in order, then there's very few places where you can go off. So it takes a bit of practice. So there's lots of practice questions available to you. But I know with a bit of work, you guys will do great.